Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. For centuries, the search for life has followed a single, unwavering rule: follow the water. On Earth, water is the universal solvent, a molecule whose unique polarity allows it to dismantle and reassemble complex organic molecules, the very building blocks of life. It's a prerequisite we impose on almost every planet we investigate. But what if that terrestrial bias is blinding us? What if the frigid, alien chemistry on a distant moon of Saturn shows that water isn't necessarily the fastest, or even the most efficient, medium for building the complex molecules needed to start life? Welcome to the Titan Lakes paradox. Titan is Saturn's largest moon, a world swaddled in a dense, orange atmosphere rich in nitrogen and methane. Underneath that smog, the temperature hovers around -290 degrees Fahrenheit. At these cryogenic temperatures, methane and ethane behave as liquids, forming vast, stable lakes and rivers across the landscape. Environments that make Earth's Arctic regions look like a tropical paradise. Scientists, eager to understand if these hydrocarbon seas could host exotic life, began simulating Titan's unique chemistry in specialized cryogenic laboratories. They modeled the core ingredients, liquid methane, and the constant barrage of ultraviolet radiation and cosmic rays that penetrate Titan's upper atmosphere. The results were not just surprising, they were revolutionary. We typically think of polymerization, the process of linking simple organic monomers into long, complex chains, like proteins or nucleic acids, as an event best facilitated by liquid water. Water's polarity is superb at ionizing molecules, making them receptive to bonding. But water also presents a major obstacle: hydrolysis. Water is too good at its job. It constantly tries to break the very bonds it helps form, forcing life to evolve complex mechanisms to protect these newly formed polymers. Liquid methane, however, is nonpolar. It is a terrible solvent for many familiar biological compounds. But in the ultra-cold, high-radiation environment of Titan, this non-polarity becomes a powerful advantage for one critical step: the initiation of complex polymers. When high-energy radiation, like the cosmic rays constantly bombarding Titan, strikes methane or nitrogen, it creates highly reactive species called free radicals. These radicals are atoms or molecules with unpaired electrons, making them extremely unstable and desperate to form new chemical bonds. Crucially, in a liquid methane environment, these radicals are stabilized by the low temperature and the lack of polar interference. Think of it this way: in water, free radicals are quickly neutralized or react with the highly polar hydrogen oxide molecules. In liquid methane, they persist longer. This extended lifespan gives them a far greater chance to collide with other organic fragments and rapidly initiate the polymer chain reaction. The polymerization process, driven by these persistent radicals, bypasses the slower, more controlled ionic processes characteristic of water-based chemistry. Essentially, the simulation showed that the initial construction of large organic molecules, the long-chain carbon structures often called tholins in the context of Titan, occurs exponentially faster in liquid methane exposed to radiation than under comparable aqueous conditions. The research reveals that methane isn't just an alternative solvent, it's an accelerator for the creation of prebiotic complexity under certain conditions. This doesn't mean life as we know it could thrive there. Water is still essential for the final folding, function, and sustained metabolism of known biology. But it radically alters our understanding of how life's precursors are assembled across the universe. If complex organic polymers, the necessary foundation upon which life is built, can assemble faster and more efficiently in the cryogenic hydrocarbon seas of Titan, then the universe might be littered with worlds that have already completed the first, most difficult hurdle toward abiogenesis, even if they lack water. This insight directly influences missions like Dragonfly, NASA's rotorcraft scheduled to explore Titan's surface. Dragonfly won't just look for liquid water. It will analyze these tholins and hydrocarbon environments, searching for signs of alien chemistry. Molecules that utilized methane's accelerating properties to achieve complexity, perhaps leading to radically different, non-aqueous forms of life. The Titan Lakes paradox forces us to expand our definition of habitability. It tells us that while water may be necessary for biological function, the formation of life's fundamental building blocks might be a universal process that functions best not only in Earth's warm oceans but also in the cold, radiating seas of an exotic, distant moon. For more incredible facts like this, don't forget to subscribe and turn on notifications.